Hi, it's Paige Kinsley. So we're currently today coming from the visualization lab at the Argonne Leadership Computing Facility. So Venkat, our first speaker, is actually going to present from here, and then we'll move on from there. But to start, what I would love, if folks are comfortable being photographed, we actually have a photographer here with us today. You can probably see the flashes. So if you're comfortable, please turn your video on. We just want to get a good picture of all of us together doing this thing that we've been doing for so many weeks. So if you're comfortable being photographed, please do that now, and we'll sort of get started. Just to sort of introduce things, sort of what's going on today. So we're first going to have Venkatram Vishwanath, who is the data science lead here at the Argonne Leadership Computing Facility, speak to us. Then we're going to have Carlo Graziani come in. Sorry, we're getting a little bit of feedback here. We good? Okay, Carlo Graziani come in, and he's going to talk. He's a computational scientist here at Argonne. And then finally, Bethany Lush, who you've actually seen before, is going to round things off. We're also going to have a science speaker, Alvaro, who will also speak to us about using AI for molecular design. So with that, I'm going to hand things over literally to Venkat, and he will get started from there.
Thank you, Paige, and it's again a real pleasure to to welcome you again to our 8th session. This has been extremely fun for us. I hope you've had a chance to use the supercomputers, learn about new and novel things of how AI is used in science. You'll hear more today about it, and tried various of the tutorials, examples on the systems here. So we're really excited, and we're really looking forward to how you would use these systems and scale them up. You have the allocations. I would love to see some scaling runs on the systems that you have here. Today, I'll be talking about some new and novel AI accelerators and how they're really impacting science. And as the audience here, you will have the opportunity here as part of the training to get on these novel accelerators and try and test them out as well. So this is a fantastic opportunity. And when I was an undergrad and grad student, I wish I had such opportunities as well. So please do take advantage of these. These are some of the systems that we'll talk about are one of the very new novel systems, which I expect to have a lasting impact on AI for science. So without further ado, let me talk. You've seen, you may have seen this before, where this talks about the progression of systems that we have at ALCF. So we started with the IBM Blue Gene L supercomputer in 2004, and where we are today is the Theta GPU and the Polaris system. These are the two systems that you have run your jobs on and done some scaling studies. Aurora, which we are really excited about, which is the 2 exaflop system, is being currently installed, and that would be, I'm hoping we can do the same set of tutorials next year with Aurora as the driving system behind it. That'll be really exciting. At the same time, we have a number of test beds that we have installed, the systems at JLSC, where we evaluate new systems. AI testbed was set up in 2020 to really evaluate new accelerators. We'll talk more about it. And we have work ongoing in trying to understand edge systems and how they integrate with supercomputers. So talking about novel AI accelerators, this is the Wild West for innovative computer architecture designs to get a really high performance for AI workloads. And what you see here is our various AI startups and companies that are designing novel chips, as well as software frameworks to accelerate AI workloads. Um, and this has just exploded. So this data is uh, from 2019. And if you look at the number of new and novel AI chips, it has just exploded beyond this. So this is a really exciting time to be working in the space of AI and systems and for science. So um, looking at all the AI accelerators, one of the key things to really pay attention to is some of them are very different from how GPUs, which are, the accelerators on Theta GPU, Polaris, um, uh, are there. So if you look at how you have a GPU kernel, and I'll talk to you some more about data flow accelerators. So what you see on top are it's a sample neural network where you're just running a couple of convolutions and um, you are doing some normalization and pooling and a sum operation. So each of these are on a GPU system is represented as a kernel. So every time you want to run this job, now I'll walk and show you this. You basically load the data and the batch and waits here from memory. You execute this kernel. You write the results back into cache. If it's larger than cache, it goes back to uh, the GPU memory. You then launch your next kernel, feed this data in. Um, if it's cached, it can reuse it. Otherwise, it has to go back to global memory to fetch it. So each operation is a kernel that needs to be launched. There's associated latencies related with launching kernels. There's latencies associated with reading data from memory and writing data back to memory. And this is a bottleneck that various AI accelerators are trying to tackle and solve. So what happens in a data flow architecture? In a data flow architecture, you take these kernels and you map them on a chip. And what you do is you take the output of a kernel and you stream that as input to the next kernel. The data flow remains on chip, and you have high-speed caches that helps move data between these kernels over here. So this is kind of a very coarse-grained approach of what a data flow architecture is. Now, the advantage of a GPU is that if you have very dynamic graphs, you can create kernels at runtime. The challenges with the data flow architecture is you need to know the graph and workload a priori. So these graphs are usually static today. There is work to make them dynamic in the future, but they really help accelerate or reduce kernel launch latencies as well as the memory bandwidth issues that you face. So we've seen a plethora of novel AI accelerators in this space. And this benefits not just AI workloads, we are seeing HPC workloads as well that can fit into the data flow paradigm. So today we'll be discussing some of these AI AI accelerators that we have at ALCF. Again, as I mentioned, as part of this tutorial and training, you have access to this. We will talk about how to do that as well. So if you want to, I'll just give you kind of a whirlwind tour of some of these AI accelerators that we have access to. So the first one is the CS2, or the wafer scale engine from Cerebras. So if you look at how we architect or fabricate these processors, you get a wafer that could be this big. you fabricate small amounts of GPUs on it. So think about each of these blocks of your being a GPU. So you could take this big wafer and you could get close to 100 plus GPUs from this wafer. What Cerebrus has done is taken the entire wafer and built an AI accelerator at the scale of a wafer. So the number of transistors that you see on this AI accelerator is close to 2.6 trillion transistors. A single GPU is in the scale of 50 to 80 billion transistors. So it's a factor of 10 difference in terms of the amount of chip area that's seen over here. So if you look at this, this tells you about you have close to 850,000, that's close to 1 million AI cores that can work on your problem. It has a phenomenal amount of memory and fabric bandwidth. This is really the key that makes these processors work really well. So close to 19 petabytes per second, which is, in comparison to what you might see even with HBM2E, there's a magnitude of difference here. So, Cerebrus is one. Another similar data flow architecture that we see is from SambaNova. This is the reconfigurable data scale unit, where you have components such as the compute units, memory units. They have an onboard on-chip switch, an address generator. So these are key components for doing data flow architecture here. So for Cerebrus, you can get, you have around 300 megabytes of on-chip memory. If you look at systems such as NVIDIA, what you have is in the scale of, I would say, 56 megabytes of on-chip memory. So this is a big factor. Beyond that, on the accelerator itself, you have 512 gigabytes of DDR memory. So on an A100 today, you have between 40 gig to 80 gig of memory. This is used for your models, for your data sets. On a SambaNova today, you have each accelerator has around 512 gigs. So you can really fit much larger models, much larger data sets, and you can reason about them. You have close to 300 plus teraflops of bfloat 16 performance, and a pretty strong support for PyTorch in this case. A third processor, which is very unique, is Grok. This is mainly targeted at inference workloads. The first two are targeted at both training and inference, whereas the Grok chip is targeted primarily at inference. And in this case, also, it's they have data that flows through a number of these compute elements. So you have some memory elements, you have you have the Western hemisphere, as well as it can go in east-west direction and west-east direction. You have some vector processors, you have matrix multiplication unit. And the goal is that you come up with a graph where you're feeding data from one set of compute units to another to really tackle your jobs. So you get around 200 teraflops plus in 16-bit and close to a peta-op in int8 as well. So again, as I mentioned, this is targeted at inference workloads. So here, here is a table that I'll leave where you can really compare and contrast these together. It talks about the various systems that we have in the ALCF AI testbed and compares and contrasts them with some of the GPU systems that there exist. So clearly you can see a lot more compute cores. It's a different paradigm. So instead of the SIMT, which is a multi-threaded paradigm that you run on a GPU. You have a data flow architecture, which is a different way of thinking about um, uh, taking your uh, graphs that you get from either your PyTorch or TensorFlow and laying it on the chip here. So our goal is to really understand how these AI accelerators can benefit science. The other goal is to really understand how do we integrate these AI accelerators as part of future system designs. So today, we have Aurora, and the system after Aurora, our goal is to really understand how do we take these chips and integrate them into really large-scale supercomputers. So that's one effort where we have work in several different directions. So again, really exciting internship opportunities here. If you're interested, please do reach out to us. These are projects that really keep me up at night in a good way, because it's full of new and novel things that you can really push in terms of push the field in new directions here. So as I mentioned, we have 2 nodes of the Cerebrus CS2. We have the first gen of the SambaNova system. As we speak, we are installing the 2nd generation of the SambaNova. We are going from 2 nodes of SambaNova to 8 nodes, which will give us 44 petaflops of AI flops here. We just installed a pod 64 of GraphCore, which is another system with very strong software capabilities, both for PyTorch and TensorFlow. We have the Habana system from Intel, and we have the Grok system as well. So in addition to this, we are constantly working with several AI vendors to evaluate their architectures and see how it can benefit science. So I'm going to talk quickly about 3 use cases for these AI accelerators and the performance that we have seen on science. The first one that I'll talk about is Supercomputing 21 COVID-19 Gordon Bell finalist. This was work that we did in collaboration with NVIDIA and Cerebrus, where our goal is to look at better understanding protein-protein interactions and how the SARS-CoV-2 protein interacts with the human host. In this case, we are really trying to understand the replication process, and this involves running massive simulations. So one key goal as part of the study is you're trying to search through this entire configuration space. And can we use AI to better steer these simulations? Was the goal of here. So we used a convolutional variational autoencoder model to take the trajectories of the MD simulations as we are evolving them and try to map them onto a latent space to see whether we have seen these configurations before. If you've seen the configurations before, we could, and these are promising configurations, we could either help them evolve, or if they're not, we could stop them and we can seed new simulations as well. So think about it as a very intelligent sampling of simulations here. So what you see in this figure is we ran a distributed training on Summit, which is a V100 based system. It's a supercomputer at Oak Ridge Leadership Computing Facility. Each node has 6 GPUs. This is V100. And we're comparing the performance of doing the training on a CS2, that's a Cerebrus system, with the Summit supercomputer. In addition, we also compared the performance of the same on Theta GPU, which has A100 GPUs. What you can see is, the performance of a CS2 is equivalent to what you could get for close to 113 V100 GPUs. And it is similar to the performance of between 22 to 32x of the A100 GPUs. So this really tells you about the impact, at least during SARS-CoV-2 times, when you're really trying to model them. And one of our key goals were to get as quick turnaround as we can for our modeling, that AI accelerators such as these could have a really impactful result in reducing the time to solution here. I have a link over here where you can read more about the paper and more about the science that's been done here. A second example is the work that we've done with Cosmic Tiger on the SambaNova RDU. In this case, we are running an image segmentation problem. And one of the big challenges that we have on the current generation of GPUs is we have to really downsample these images for training. So in this case, we are running at 640 by 1024 to train it on a A100 GPU. And like I mentioned, one of the key architecture of SambaNova is that it lets you, it has around 512 gig of memory on the accelerator, and you can run at native resolutions. So we've been able to run native resolutions for this neutrino physics image segmentation problem. And we achieve state-of-the-art for both state-of-the-art performance in this case. And again, more information is available at this publication. So yet another use case when you are working with large-scale imagery. One use case for us is we work with the advanced photon source at Argonne, as well as with data sets from electron microscopy. So the connectomics example that Nicola Ferrier talked to you in the very first session, if you remember, each slice is 80K by 40K pixels. So that's the kind of scale that we really need to tackle. And we're not there yet. But architecture such as this, coupled with model parallel and distributed data parallel training, can really help us tackle data at those resolutions. The third use case I'll talk about is work that we've been doing with the Grok system, both for forecasting plasma instabilities in tokamak, as well as with screening billions of compounds for COVID-19. The work over here is one that that we worked with Grok to understand the inference problem. The tokamak problem is one that Kyle Felker, whom you know and have worked with, is closely associated with. I should mention that the previous one in Cosmic Tiger is one that Corey Adams, who presented, has been working and scaled this to a number of supercomputing systems. So, you can read more about, we can provide you links about the code as well. So Kyle and his collaborators at Princeton Plasma Physics Lab have been working very closely with on trying to understand and forecast plasma instabilities here. And the key goal for them is before an event of interest occurs, can we predict that? And within a millisecond of response of latency, respond to those events. So the key performance metric is to have a latency of a millisecond. So if you run today in an inference mode, both on an NVIDIA A100 system with a batch 1, as well as with a batch of 256, you get in the range of 3 to 5.5 milliseconds. I do have to point out that this is with FP32, and there are ongoing efforts to try at much lower precision, and there are other optimizations that can be tried here as well. On a Grok system with FP16, for a batch one, you're able to get it in 0.14 millisecond, which is much lower than the 1 millisecond that the initial target was. So these are really promising results if you want real-time or near real-time feedback for scientific experiments. Another use case is the work that we did with trying to screen through molecules for COVID-19. And the goal was to understand the efficacy of these molecules and whether they meet a target property. So as we try to screen through a really large database of these, again, the higher the throughput, the better the performance in this current use case. So, if you normalize it on a V100 performance as 1, you get around 1.7x improvement on a A100 in comparison to the V100. If you run it on a Grok card in FP32, you get about a 185x improvement. Again, and this is primarily because you're running through data and you're running through a number of models, and there's some on the Grok card, the data flow architecture together with its abilities for co-resident models are some of the key innovations that we have here. And FP16, you get again another order of improvement there. And this basically, demonstrates that these are really promising results. And as we architect next generation systems, AI accelerators and these architecture features are going to play a key role for future systems. So with that, I'll thank you for all the exciting work you've been doing. If you go to the GitHub page, I have 2 links there. The first link will provide you information about the ALCF AI testbed and how to get started. We have in-depth documentation on our ALCF AI testbed page that provides you with how to run through examples and how to even port your application to run on these platforms. So we have the Cerebra system that's available for this class, as well as the Sabanova system. On the Sabanova system, you have support for PyTorch. On the Cerebra system, there's support for TensorFlow Estimator today and initial support for PyTorch. So I would say that you should use this as an opportunity, given that you have an allocation. This instruction, your regular ALCF account that you use for Theta will get you up and running on these systems there. You should give it a whirl, and we would love to hear feedback. And as I mentioned, these are great topics for internships, and we are always looking forward to pushing the limits of science here. So thanks again.
All right. Thank you, Venkat. So now we're going to transfer things over back into the virtual world to Carlo Graziani. Carlo is a computational scientist here at Argonne National Labs. His background is in physics and astrophysics. And today he's going to talk to us about Gaussian process modeling, the other AI method. So with that, I'll hand things over to Carlo.
Okay, very good. So first of all, am I audible? Can you hear me?
You sound great.
Good. And is my screen visible? That's the other check.
Yes, it is. We see the Jupyter notebook.
Okay, very good. All right. Well, thanks for inviting me to give this talk. Gaussian process modeling. Some of you may already know a little bit about this, but it's actually one of the is really rather an old type of AI. In fact, it was a method that was in use well before anybody thought to call it artificial intelligence. It dates to the works of Norbert Wiener and Kolmogorov in the 1940s. There's really, if you're interested in looking more deeply into the subject, I can't do any better than to send you over to this book by, Rasmussen and Williams has really turned a lot of people onto this subject. There's this book, Gaussian Processes for Machine Learning, and these people, bless their heart, they made the book available online from the very beginning. It's available at this URL. By the way, this Jupyter Notebook is available we made available on GitHub. So you can download the whole thing or just check it out directly on GitHub. And the book is just fantastic. It's quite rigorous, but it's also very, very accessible. So they don't beat you over the head with the epsilons and deltas, but all the material is definitely there. So what is a Gaussian process? You can think of it as you're all probably familiar with what a multivariate normal distribution is. So if you think of transferring the idea of a multivariate normal into an infinite dimensional vector space, then you'll more or less have the right intuition for what a Gaussian process is. And if you've ever, studied quantum mechanics in your life, and you're familiar with the idea of a Hilbert space, or on the other hand, if you've ever had to do a Fourier analysis of a time series, then you know that a good way of thinking of a Fourier series is as basically an expansion of an infinite dimensional vector space of functions. Then placing a Gaussian distribution over one of these spaces of functions also gives you a good intuition over what we're talking about here. A Gaussian distribution over a space of functions, if you think about it, is rather a powerful way of analyzing data, because it gives you a way of saying, look, I have these data, I have these function values. I'd like to know what they tell me about the underlying function that gave rise to this data. I make some assumptions about a space of functions, and I'd like some uncertainty estimates over what this function might look like. That's what this distribution tells you. It tells you something like, what is the mean function that this could have come from, and what kind of uncertainty can I ascribe to this sort of function. It gives you the ability to sample functions from this Gaussian distribution. It's a seemingly harmless generalization, but it actually has these surprising superpowers, because you can train the Gaussian process to, based on some data, to give you, based on an agnostic initial distribution, to give you an updated distribution over functions that captures the information that you gave it. And you can make probabilistic predictions based on that updated distribution about the values of the function at new untried settings that you never showed it before. So this is kind of a very powerful methodology. And so now let me also say something that maybe is a little bit invidious with respect to some of the AI methods that you've been seeing throughout the course of this training course, which is that Gaussian processes come with a lot of very well-developed mathematical theory, which is, not really so much the case with a lot of artificial neural network methods that you've seen, which often have the character of being, somewhat, ad hoc and engineered and put together for the purposes of whatever immediate problem that has happened to come to hand. Gaussian processes really have a lot of very principled mathematics, and they really come with no interpretability issues. They're basically just a mathematical tool, and it would never occur to you to ask interpretability questions of these tools any more than you would ask about the interpretability problem of a hammer or a screwdriver. And the final thing is, if you've encountered Gaussian processes at all before, and you've heard that they're really too expensive to use in the age of big data because the scaling basically makes them unapproachable, then as I'll tell you by the end of this talk, I have some very good news for you. So we'll get to that by the end of this talk. Okay, so what I want to try to do is maybe develop some intuition for how Gaussian processes work, and sort of come at this from a direction that even if you have seen Gaussian processes before, maybe you haven't seen this perspective on why they do, why these largish claims that I've made for how they work, how they, how they can do the kinds of things that they do. So, I'll do this by sort of appealing to some of the properties of Gaussian processes that you're probably already familiar with. So let's start with some of the things that you already know about Gaussian distributions. So in a finite dimensional Gaussian distribution, you're probably already aware, in d dimensions is described by a probability distribution function that is defined by two algebraic objects. One is a mean vector, x naught, and one is a d by d matrix, a symmetric positive definite matrix, covariance matrix. And symmetric positive definite basically simply means that it's a symmetric square matrix, all of whose eigenvalues are positive definite. And if you have these two objects, then basically its density is given by this kind of formula, which I think most of you have already seen before. And this structure can be displayed pictorially by this sort of picture, in which the mean has this sort, you can show it by this point representing the center of the distribution, and the covariance can be described by this sort of ellipsoid that represent, you can think of it as perhaps being the 1 sigma ellipsoid of the distribution, in which this basically represents the eigenstructure of this covariance matrix, in which the long direction represents the direction of the this is in 2 dimensions. So the long direction would be the direction of the larger variance, the larger sigma, and the short direction would be the direction of the shorter variance, the shorter sigma. Okay. So now suppose I do the following thing, now to get to how training for a Gaussian process, or even just for a Gaussian distribution works. Suppose this axis is x1, this axis is x2, and I do the following thing. I observe the value of x2 while not observing anything about x1. How would I depict this situation? Well, I would depict it like this. I observe this value right here, and I say, okay, I observed it to be 1.8-ish. I observed this value. It's a little less than 1.8. So if I observe this, have I acquired any information about x1? Well, the answer is yes. If I knew this distribution and I observed this value exactly about x2, I have acquired some value about x1. This is what in fact what happens, because I've restricted the information that's available about x1 by changing the probability distribution about x1, conditioned about my new information about x2. And this is pictorially what the new situation looks like, right? I have a one-dimensional distribution. My distribution on x1 conditioned on x2 is, of course, no longer a two-dimensional distribution, it's a one-dimensional distribution. And you can see what's happened. The mean of with respect to x1 used to be over here, and now it's gotten shifted over in this way. And the variance with respect to x1 that used to be this big wide thing has now gotten shrunken, to this narrow thing over here. And the key thing is that these two things, this shift in the mean and the shrinking of the variance, are computable in closed form. They're just, I'm not going to show you these formulae because there's, life is short. But I just, believe me, and you can look them up. These formulae are just computable in closed form, and they're just a romp through linear algebra of, you can compute them in terms of the covariant and mean function that vector that I showed you earlier. Now, this is just a little silly example that is helpful for visualization, but I can make the same kind of observations if I change this two-dimensional example, or if I change D to be large but finite. And if I partition these coordinates into two disjoint sets, so into a set XO, I'm going to say O for observed and I for ignored. So DO and DI, such that they sum to D. Okay, and so I observe XO and I don't observe XI. I can still compute the distribution of XI given XO. And the exact same thing happens that happened here, which is I get a conditional distribution of Xi given XO, in which the mean of Xi gets shifted over because of the information that I've added by observing XO, and the width of Xi gets shrunken way down because of the information that adding information always reduces the variance. This is one of these, it's a deep fact from information. There's actually a subject called information theory that dates to a guy named Claude Shannon, who invented it in the 40s. And it corresponds to the fact that when you add information, you shrink the variance. And that's what happens here. The variance in Xi shrinks down. Or you could compute the variance of any subset of the Xi. I don't have to compute all of them. I can compute only a few of them. There's this fact that any linear function of a set of Gaussian variables also has a Gaussian distribution. So if I don't compute the distribution of these Gaussian variables, but I compute the distribution of some linear functions of them, I also get a Gaussian distribution. So if I observe some, instead of the Gaussian variables, I observe some linear functions of those Gaussian variables and compute some of these x's based on some observations of some linear functions, or I observe some subset of them, I'm going to get the exact same situation that I had before. Okay, now what's happening here is I'm trying to build towards something. These are not some random disconnected statements that I'm making. I'm trying to build an intuition towards why Gaussian processes work. So please bear with me. There's a point to all of this. So finally, there's the Gaussian process case, which is I'm trying to build towards the infinite dimensional case, and because that's where functions live. Functions are basically live in infinite dimensional spaces. And I get there by letting the dimension of the space go to infinity, with the number of observations remaining finite. And in that case, I compute the the distribution of a finite subset of variables. And I have this exact same situation. Okay, I'm going to be able to compute with some formula that I have access to the distribution of some finite set of variables based on some finite set of linear observations that linear functions of these variables. Now, let me make just a quick side. This will turn out to be crucial. I just want to make a little side observation here that has to do with hyperparameter observation, which is I don't want you to feel swindled here, but note that I did start with this covariance and this with this covariance and this mean, with this mean vector and this covariance matrix. And you might ask, well, where did those come from? I just pulled them out of, I pulled them out of the air, but who gave them to me, right? Where do I get them? Well, suppose that I've measured some these linear functions of x, and I wish to set out to make some probabilistic estimates of some variables. In any of these cases above, but I don't necessarily know the right mean and the right covariance. How am I supposed to proceed? Well, one way to do this is I could start with a whole family of such means and a whole family of such covariances that are parameterized by some set of parameters. Okay, then what I can do is maximize the log likelihood function. And my guess is that you've already seen such objects in some of your previous classes. The log likelihood is just the probability of the data given this parameterized model. And there's a formula that, that I can write down straightforwardly, given that these are all Gaussian models. I can write down the log probability given this mean and this covariance, and I can maximize that log probability with respect to the parameters and obtain the maximum likelihood estimate of the theta. Okay. In the Gaussian process case, the parameters are usually referred to as hyperparameters, and we do this to distinguish them from the ordinary case of fitting parameterized models in which we have functions of families like, what am I, dyslexic? I mean, families of functions like polynomial functions or exponential functions, where I specify the functions, the family of functions explicitly. In Gaussian process modeling, what I'm doing is I'm not specifying the family of functions explicitly. I'm specifying functions by their characteristics, such as their scales or their curvatures or their by their broad characteristics, by the character of their Hilbert spaces. And so these parameters are referred to as hyperparameters. And I'm only making a federal case about this because hyperparameters are used in the context of Gaussian processes in a sense that is a little bit different from the way that term is used in the context of artificial neural networks, where they're generally used in a more discrete sense, having to do with things like perhaps the number of layers in a neural network, or the type of the type of activations that you use, things like that. Whereas things like actual parameters are referred to as parameters. In Gaussian processes, parameters that you ascribe to things like covariances are referred to as hyperparameters. It's a different kind of usage, and I think it's a cultural distinction between how statisticians use language and how computer scientists use languages. Use the language. It's something that one runs into actually. One runs into these cultural distinctions rather often, in fact.
Hi, Carlo. This is Paige.
Yes.
So I think I'm just going to hit pause for a brief moment. So we usually take a break, give students about a 10-minute break so they can sort of stretch their legs. So I was wondering if you have a place to stop, pause, wrap up.
We can stop anywhere you like.
Okay, wonderful.
Right here. I have a little horizontal line right there, and we can move on to functions right after this.
Perfect. Okay, so folks, as you know, we'll give it we'll come back at 4 p.m. Eastern, so give about an 8-minute break, looking at my clock, and we'll come back and we'll hear from our science speaker first, and then jump back into things with Carlo after that. So with that, we'll come back in about 8 minutes to hear from Alvaro and continue on from that. So now we're going to shift to our science talk for today. So today we have Alvaro Vázquez-Mayagoitia, who is a principal software development specialist here at the Argonne Leadership Computing Facility, with a background in computational and theoretical chemistry. And today he's going to be talking to us about the impact of machine learning on molecular science, sort of giving us an overview of that. So Alvaro, I'll hand it off to you, let you share your screen, and we can start from there.
All right. So, no, thank you for allowing me to speak in this last session of this training series. I hope you enjoy this workshop. I think it's unique. I know it was like a fast-paced training, you know, I hope it's just the beginning of your interest in data science. So I just want to acknowledge our laboratory, our facility, and the Department of Energy who sponsors our work. So you may be overwhelmed when you think in supercomputers and exascale, right? So just 2 floors below where this meeting is streamed, there is a exascale computer under development, which is called Aurora. And as you saw in Venkat's presentation, so these computers have like millions of cores and are capable of solving 10 to the 12 operations in a second. So it could be overwhelming, but still, believe me, that's not enough, right? So for the amount of information that is out there, these are peanuts, believe me. So as you have noticed, I mean, as you might know, there is something called the Moore's law that says that the number of transistors on the chips are doubling every 2 years. The truth is that there will be a limit in the size and also in the electronics for this element. So this is, I mean, they call it a law, but it's not a law. I mean, it's just a principle or whatever. So this curve will slow down in the coming years. So that's the reason that we are exploring new technologies to do the computation. Still, why I told you that these are just peanuts. So if we see, for instance, the number of the number of the bases, the nucleic bases in the DNA that we can sequence per day, right? We are speaking of about trillion of bases that we can sequence per day. So the amount of information that we are extracting from the DNA is surpassing the amount of information that we can store in hard disk or process in the computers. And this different. So what I'm trying to tell is that we don't have enough computing power and enough memory to store all the observations that we are getting from the nature every day. Indeed, the efficiency of the research is slowing down. So every time is more difficult to get new insights and produce new materials, new drugs. There is something called the E-room, which is the opposite to the Moore's law, that says that the cost of developing a new drug doubles every 9 years. So it's every year it becomes more and more difficult to produce new drugs. Actually, many of the drugs that we saw, for instance, for COVID, or we try to investigate for COVID, are just old drugs that we try to repurpose them, right? So, and this is what actually is happening nowadays. Is the effort to produce new materials is so time-consuming and so expensive that what we are just doing is taking the old materials and trying to tweak them to solve new problems. This is what's happening with the drugs. So the drugs, now we found new properties for all drugs, and now we mark them as a new, but actually are old, right? Anyway, also the number of publications that are increasing every year. So we are not just having problems to find new things, even producing. So we are producing information and a very rapid pace. So that's the reason that we should be using something smarter, right? Using AI to solve problems that we see in the nature, right? So simulations are complementary, but it's just foundational. So what we need is now to find guidance from AI. In terms of the chemistry, so yes, every year we find about 50 million new compounds that are added to public databases. So this is the plot of number of substances against the last years in the ACS CAS registry. ACS is American Chemical Society compound registry, and so the new materials have been aggregated at a very fast pace, but it's still not necessarily new materials means that they are more useful, right? So this could be a misconception. So I mean, if you have a new material, you want to see that this can be applied to solve a problem. When we see the spectrum of the material sciences and the methods to study them, so we can study the materials from the atomic perspective up to the macroscopic perspective. So from the atoms to the actual, for instance, membranes or cells, right? But between these two endpoints, we have multiple scales where you go from hundreds of atoms or dozens of atoms to hundreds to thousands to millions. And if you want to compute them with accuracy, really, if you want to really accurate methods to study these materials, maybe you can afford systems with very small atoms. So if you study carefully this plot, you will notice that there is a big gap between thousands of atoms and millions of atoms, and casually is practically the border between studying systems with electrons and no electrons. And also there is a gap, an horizontal gap that I don't paint here, which divides the accuracy part. So what many people have thought is like maybe AI also can bridge between these layers, right, in the spectrum. Anyway, in general, what I want you to learn today is, or be aware today, is that the property of the materials depends in the number of atoms in the materials and the position of these atoms. So the structure is what determines the property. And when I say structure, is again the number of atoms and electrons, of the particles, and also how these the systems are arranged. So here the secret to use machine learning, I want to speak from the optimistic level. The secret to apply machine learning to AI is the ability to translate from the chemical object to something numeric that you can input to your neural network or to Gaussian process model. So how you transform this molecule into numbers? Well, there are many approaches. One is applying descriptors. So there are manuals of descriptors with thousands of different descriptors. Some of them are good, some of them are not, all depending on the application. And also, you can apply, for instance, fingerprints or kernel functions. So with these two paths, that you can create fingerprints or uniqueness, or on objects that are unique to represent the molecules. There are other approaches where you can, for instance, represent this with networks. Also, you can apply, some people have applied something like natural language process. So you say, well, the molecule is like a sentence, and the atoms are the words. So you can also apply this kind of things. So but the key point is that whatever you use should be should be unique. So for the system you want to apply, and unique in the sense that not only represents represents the molecule, but also is invariant to translations and rotations, and can capture the differences between the distance of the atoms and the positions. So we have applied these problems using Gaussian simulating the atoms, the potentials or the interactions between atoms using Gaussian functions that come from a Gaussian regression. And we can create models for atomistic simulations or atomistic interactions to study, for instance, later to use them to do molecular dynamic simulations, and for instance study the X-ray spectra, or to explain the X-ray spectra of materials, or also the thermal properties of, in this case, two-dimensional systems like graphene. Also, we have be able to combine simulations and experiments. So this is something very powerful, where you can combine the best of previous knowledge and select your training set to produce models to predict the properties. Another approach, so the approach that I just talked to you is atomistic. So we just go directly to the atoms and how the atoms interact. But also what you can just say is like, well, I don't care exactly where the atoms are located, but I want to know the properties of the atoms, and just let the computer to understand what are the most important features of the molecule. So probably in previous sessions, you studied principal component analysis, or even better, you might see in the autoencoder sessions how to reduce the dimensionality of data sets. So in this case, I'm just showing a plot of the NIST data sets for the digits from 0 to 9. And so this just to give you a reminder of how this looks like, right? Now the computer automatically is distinguishing the groups for the corresponding digits in the data set. Something very similar could be applied to molecules. And also, so in this case, you have an autoencoder that translates from SMILES. SMILES is a way to represent molecules. And then, so in a autoencoder model, you can create a latent space and even move in this latent space to find the properties that you want. So this is very powerful if you want to explore new molecules, right? Or try to understand what kind of features of the molecules are the important that produce the property that you are looking for. A practice that is borrowed from bioinformatics is the funnel approach to, to screen and discern from millions of atoms, and then apply multiple filters or rules to discriminate the most important, because so as I show you, the chemical spaces could be vast, could be there are many orders of magnitude size, but you really want the molecule that will solve your problem. So what you have to apply is a funnel approach and rules. And also one way to do that is, for instance, applying different levels of theory or physics models, right? So in each layer of this funnel, you can just apply. You start from cheap models to very expensive, and then get the last one. So this, you might see this like an AI, but you can harness this process with AI, for this high-throughput tuning and data-driven approach. Another very another approach to explore the chemical space is trying just to find information from literature. So what we are doing at Argonne with some partners from Cambridge University is to extract information from papers. So what we do is we apply natural language processing to the text. Our methods are able to, follow acronyms along the text, and also identify chemical compositions and properties. So this is a very powerful way to get extra data for your data science and AI projects. Indeed, I apply something. I apply these methods to study solar cells. In this case, I studied solar cells that are called dye sensitized. So these are just dyes that are surrounding particles that can be embedded in solar windows. So you can use this as a windows for buildings or skyscrapers and or houses or doors or wherever you want, and produce electricity. So these windows are in Switzerland. This is a conference center that exists there. And so the problem is that no one knows which dye is the correct one, right? So what we did is extract dyes from a data set, and then we created maps to identify the most important features of these molecules. We did prediction of the properties. So here I'm not taking the atoms, individual atoms of the molecule. I'm just taking at the high level the properties and the systems. And then I managed to have with Gaussian regression a model that is capable to give a really good estimate of the excitation energies associated with those dyes. So we managed to produce, to find two dyes, right? So the problem with the solar spectrum is that it's very broad, right? So this, you have just a collection of wavelengths. So what you want, yes.
Hi, it's Paige.
Yes.
So I think we're running into time, so I don't know if
sure.
you have sort of just a final thing to say
yes,
about all things.
this was the last slide, and thank you so much. So with this project, we found an excellent dye, a couple of dyes that are really good absorbing light. Yes, so Thank you for listening. Let's switch to the Q&A.
Yeah.
Yeah.
So I think we actually have a couple of questions in Slack that are really, really specific for the student to you. And so I think because of time and also because of the nature of the questions, I think I'll follow up offline for you so we can connect you
Sure.
and Jared, because he's interested in potentially doing research and finding an internship in this specific field. So
Great.
good to connect. But with that, we'll transition back to Carlo for his hands-on activity. So thank you so much, Alvaro.
Okay, very good. Okay, so yeah, I'm going to move basically directly into the activity here. And to introduce that, I just need to tell you what a Gaussian process is in practice. In order to specify a Gaussian process, you need to specify a mean function, which is the analog of a mean vector, and that's basically just a function from a space into the reals. A covariance function, which is a symmetric positive definite function as an integral kernel. And this basically just gives you is a way of selecting certain choices of the function space that you're going to be operating in. And this is just a list of the kind of properties that you might decide that you want to specify. And the last thing that I just want to tell you here is that it was thought until very recently, and many people still today believe that Gaussian processes are basically just not a contender in the big data space because they're this horrible scaling, which is n cubed associated with a linear problem that you have to solve, where n is the number of data points that you have. And so they punish you for trying to do the right thing. You add data and they just get worse and worse and worse. And it turns out that that's no longer true because there are these modern fast kernel approximation methods that have changed the scaling to n to the 0. And at ALCF, we're now rolling out this library called gPyTorch that is the basis for this activity that I'm showing you here. That basically both takes advantage of the scaling and also, since it's based on top of PyTorch, avails itself of PyTorch's GPU acceleration. And so what we're really looking forward to is having large Gaussian process computational loads basically happening at HPC scales, really for the first time. We're hoping to basically lead this facet of AI to HPC and really surprise a lot of people this year. Okay, so this is the activity, and if you like, those of you who are on and this is basically going on Jupyter Hub, and those of you who are basically following along for the fun can basically click along. I don't know how you guys have been doing this, but anyway, if you basically start clicking, it's basically just a click along. So this is basically the gPyTorch interface. And what we're basically going to do, this is basically adapted from the gPyTorch tutorial. And here what we're basically going to do is we're going to start by creating some training data. And the training data is basically just going to start by creating some points in 0 to 1 and create, a point for create some targets from a sine function with a little random noise, from basically some little additive Gaussian noise. So if we basically run this cell, that there, our training data is made, and we've also basically, as you can see, imported the usual suspects here. So that that was trivial, and now basically what we're going to do is we're in this section. Basically, we're going to do what I told you, which is we're going to set up the Gaussian process infrastructure according to the API requested, the API of the gPyTorch, And here what we're going to be doing is setting up a covariance kernel function and a mean function. The covariance is basically the squared exponential. Sometimes people sort of refer to this as the RBF or radial basis function kernel. It really should be called the squared exponential covariance. And it's done in this way because that's what's required by the API. It's really, you really should go and read the documentation. It's complicated, and we don't really have time to go into why they do it that way. The only other thing to explain is that this likelihood line over here handles the model handles the actual model representing the function. The likelihood handles the modeling of the noise that's added to the function. And we'll see a little bit of the aspect of that later on when we see the prediction part. Okay, here we come to the training. Training actually has two meanings in this context. There's a training where we actually adjust the hyperparameters in the covariance and the mean, and then there's a training in which we actually fit the training. We do the conditioning on the training data in order to predict out of sample. So the training basically follows a similar paradigm to the artificial neural network training, and it has basically the same components as a PyTorch training loop, which is you zero the parameter gradient. I'm sure you've seen this before. You call the model, compute the loss, and then you call backwards on the loss to fill in the gradients, and you take an optimizer step. So if you look at this loop, I'm sure it recalls things that you've seen before. So now I'm going to basically click through this, and you'll see what happens when we go through. You're going to see the familiar. Here's all the it's going through the iteration and printing out a few key things. What we're seeing here, incidentally, is this is the length scale, and the length scale is remember that the function that we printed that we evaluated is this sine 2 pi x, and the length scale is the length scale of this 2 pi x function. And if you think about it, it's basically 1/4, basically a quarter wavelength. And what we came out here is actually not too far from that. It's almost a quarter. And you can see that it's dropping. So we probably could have gone on training a little bit, but life is short. We don't want to actually, go on till the 7th significant figure. We added a noise term on the order of 0.04. It got to, maybe it dropped a little bit below that. It got within range. Maybe it overshot it a little bit. Okay, so let's get to model predictions. What do model predictions look like for a Gaussian process? Well, what we're going to do is we're going to make some test points in which we're going to request the predictive distribution, at which we're going to, son of a bitch. Oh, pardon me. Was that allowed? Sorry, my connection died. I should go back and reconnect. Bethany, do you want to go forward and do your part while I reconnect to this kernel?
Okay, so our topic today is advanced AI architectures and AI methods. So Venkat showed you some AI architectures on the hardware side, and Carlo showed you about Gaussian processes, but I want to also talk a little bit about some other methods that we don't have time to cover, to give you kind of an overview of what's out there. And sometimes it can be really helpful to even just know like these things exist or what they're called, just so that later when they become relevant, you know what to Google. So to recap, in the first week, we did linear regression and k-means clustering. And then in the subsequent weeks, we did neural networks, specifically for image classification. So in the broad scheme of things, if you think of machine learning as being within artificial intelligence and deep learning being a method within machine learning, we've been in this little purple region most of the time, and specifically image classification. And today we're also talking about Gaussian processes, and I'm going to talk a little bit more about what else is in these circles. But in weeks 2 to 7, we did increasingly complicated versions of neural networks for image classification. And I'm going to say the homework now so that you keep it in mind while I'm talking. The homework is to submit a paragraph about how you could use AI for some problem that interests you. So like, what's the machine learning task? What kind of data would you need? What kind of method or model might be appropriate? And how would you measure success? Like, is it accuracy? Is it, something like that. And you can feel free to look online for papers or blog posts or something that might be relevant. So that's motivation to listen as we talk about some other advanced methods. And I'm going to talk about some broad categories. So what we've been talking about so far primarily has been classification. So you have a category label for each data point, like you have a lot of images and you learn how to categorize a new image. And a science example could be label X-ray images with a diagnosis. Now, in machine learning context, people sometimes use the word regression in contrast with classification to mean that you're predicting a real number instead of a class. So something like you're predicting stock prices after you saw historical stock data, or you learn to predict the melting point of a molecule after seeing lots of experimental data. And we saw in the first week clustering. So you have an unlabeled data set and you want to find groups of similar points. So in the tech world, this could be something like finding communities in a social network. In a science context, it could be something like subtypes of breast cancer. And another cool area of AI is reinforcement learning. In this context, you have an agent exploring some environment and it wants to get rewarded, but it's like a delayed feedback. So an example, a real example, is people trained AI to play Frogger or other Atari games. So you're playing the game and your delayed reward is your score in the game. And a science example of using reinforcement learning could be something like suggesting useful chemical reactions. So this is different than I'll talk about the term supervised learning to remind you, but this is different than, let's say, regression in the sense that you don't start with a bunch of input-output pairs. You just have the agent explore and it gradually learns what's good and bad because of this delayed reward. There's also, we all encounter a lot of recommendation systems, like recommending a movie to watch on Netflix, or a science example would be recommending a scientific paper to read. This is what Google Scholar suggested to me today, that they think I should read. And this can be separate methods than some of these other machine learning tasks. And something that probably a lot of you, like me, have been playing around with is generative modeling. For example, generating an image based on a text description. Here's an example from DALL-E 2 from OpenAI. Or in a science case, this could be something like generate a super resolution version of this physics simulation. And we touched on this vocabulary before, but I wanted to lay it out explicitly and remind everyone. So supervised learning refers to when you have labeled data, like input and output pairs. So like classification and regression are definitely supervised learning. In unsupervised learning, you have unlabeled data, and clustering would be an example. And semi-supervised learning could be you have a mix of labeled and unlabeled data to learn from. And here are some examples of other AI goals. Like searching through many solutions, like a robot trying to figure out how it should complete a task, doing automated reasoning, like theorem proving, natural language processing, like writing an essay based on a prompt. That's been, I know a lot of people have been having fun exploring those kinds of models lately. Perception could include things like speech recognition and computer vision. Speech recognition has gotten so accurate now with speech to text on our phones. Dimensionality reduction, so something along the lines of compression, like you want to find some reduced representation of your data in the context of physics. This could be something like the primary modes in a fluid simulation. And anomaly detection, so something like you're in cybersecurity and you want to flag suspicious things happening on the computer networks. And this is not covering all possible AI goals, but just to give you an idea that there's more out there, and some of the vocabulary around it. Okay, so now I want to talk about some methods for approaching these tasks, and again, just a high-level overview. Now, there are a lot of variants of neural networks. As I mentioned, so far we've focused on neural networks that do image classification. They had convolutional layers. If you want to do time series prediction, you typically have what's called a recurrent neural network layer. And there's some special kinds like LSTM and attention. I'll talk about that more on the next slide. But if you're interested in experimenting with this, under the bonus material folder, we have this images time series example. And the fancy, cool new thing is transformer models. There are also versions of neural networks to incorporate known physics, like invariances that you know, symmetries, conservation laws, or if you know a PDE and you want to constrain your neural network to follow it. There are methods like PINs, physics-informed neural networks. If you're interested in this in the bonus material folder, you can see this physics-inspired AI folder. And those two under bonus materials are topics we covered before last year, so you can also watch the corresponding video online. As I mentioned before, I mentioned that there's the task of generative modeling, and some variants of neural networks for generative modeling are generative adversarial networks, or GANs, which I have another slide on, or the newest thing that's very successful this year is diffusion models. If you're working with language, you can think of as a sequence, like you've got a sequence of words or characters. So it's also often some kind of recurrent neural network, and what's referred to as large language models are using transformers, like I mentioned above. And for dimensionality reduction, one approach would be an autoencoder. Autoencoders have outputs that match the input. The input to your neural network should be the same as your output, which sounds trivial, except that you have typically you do something like have a layer in the middle that's small. So that's forcing the neural network to find a low dimensional representation and then reconstruct the full dimension. So just to say a little bit more about recurrent neural networks, a basic recurrent neural network looks something like this. You input your data at time t to some little module, like let's call it A, and it gives us a hidden state, and then you apply that recursively. And if you kind of write that out in an unfolded way, that's what we have on the right. So let's say you put in the first part of your sequence, this module of your model gives you the first hidden state, you put in the next part of your sequence that gives you another hidden state, and so forth. And so you can then build on that to have this internal representation of some history. But there's a lot of fancier variants on top of this. And I wanted to say a little bit more about generative adversarial networks, or GANs. You have two neural networks. One is a generator, and it takes some random input, which is called Z here, and then it has to generate some realistic examples. So if the task was to generate handwritten digits, then this generator attempts to generate some handwritten digit. This other network, the discriminator, is trained to say, is this image a real handwritten digit or a fake one? And you're jointly training the two of them so that they both get better. And your generator starts to learn how to generate something that can fool the discriminator. Now, that was more about neural networks. There's also what some people call classical machine learning, which is like things other than neural networks or not deep learning. And a lot of those methods are in the Python package scikit-learn. And I think this is a cool cheat sheet they put up there. They have you follow along this path. And yeah, if you have a small amount of data, get more data, so forth. And it breaks it down into some of these same categories I was mentioning, like classification, regression, clustering, and dimensionality reduction, and then suggests which algorithm to try. And this flowchart is a decision tree in that you start somewhere and then asks you a question, and then you branch depending on your answer. And I mentioned that because decision tree is an example of a machine learning model. You go down the tree and it keeps splitting based on one feature, like one, let's say you described that, or on the task of predicting the value of a house, and you describe the house as like number of bedrooms, number of bathrooms, square feet, things like that. You keep branching based on those features. And this can often be helpful for features that are not continuous, like especially if they don't even have an intrinsic order. And then it's even better if you have a whole group of them, a whole forest of them with some randomness, and that's like having a bunch of trees vote. So that's in the scikit-learn library, and you can see that in the cheat sheet. Okay, we're running a little low on time, so you can check later if you want. I talked a little bit about genetic algorithms and some other approaches to help you in your machine learning, like automated machine learning and improving your data set. So in conclusion, AI has a lot of applications, lots of new methods. Supercomputing can help you with your large data sets and models, and there's a lot left to learn and explore after this training series. And I can pass it back to you, Carlo, and I can check for questions and stuff.
Okay, very good. Okay, it's me again. Hopefully this time, for the last time. Okay, this is where we were, and we were going to test the predictions of the model that I was showing you about. So without further ado, let's make this set of points with support both inside the training set, which was inside the interval 0, 1, and some outside of it, which is from 1 to 2.5, and see how the model did. So let's just let this thing go and see how it does. Okay. Right. Yes, of course, has to run the whole thing. Dun, 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 dun. Hello. Here we go. All right. Now we're cooking with gas. Okay, so this is what it did. What you can see is that here's the train. So it updated the hyperparameters from the original ones to updated ones, and then it basically trained a mean, which is this blue curve, and you see that it basically goes through the data, and then basically it settles back onto this basically back to zero, which is basically the prior value. That's the mean of the prediction. Okay, then there's this inner snake, this blue shaded area over here. You can barely see it. It represents the variance of the latent predictive distribution. What that means is what you would see if it were possible to strip away the noise and see the underlying process. So often that's what you really want in a Gaussian process model, is you model both the model and the data and the noise so that you can tear the noise away and see what it's doing underneath. The pink snake is basically both of them. There's both the model and the noise model together. These bounds basically represent a 90% confidence interval. Okay, now to the right, so this is the interpolation region. This is the extrapolation region. Okay, and here what you can see is this property of Gaussian process modeling. The model is basically honest about what it knows and what it doesn't know. As it leaves the data where it trained, it's basically telling you that the uncertainty basically grows until it's telling you, okay, we've gone far enough from the data that I don't even know very much about what the data would be doing here anymore. And all I'm going to tell you is what I learned back here from the whole range of variance of how much the data was varying. That's all I'm going to tell you, because we've basically moved we've moved too far from the domain of support of the data. So basically it's not willing to be overconfident about the data, which is actually a nice property of Gaussian processes. They actually warn you, when you move away from the support of your training data. Gaussian processes are not overconfident, which is, you should be aware that not all machine learning models have this property. Okay. All right. Well, that's basically it for Gaussian process modeling. The conclusions are, it's been around for a while. It provides a powerful framework for modeling data with underlying spaces of functions. And what's new and exciting is the possibility of using them at high performance computing scales. And this is going to start happening at Argonne this year on Polaris, and next year on Aurora. And for this, basically watch this space. That's it. Thank you.
Thank you, Carlo. All right. So that is the final content that we have, but I'm going to share just a couple slides sort of as like final wrap up of things. So y'all sort of know what to think about next. The first thing is resource access. This has been asked about in Slack. Your ALCF accounts to get onto Theta GPU or the AI testbeds are active through the end of this year, through December 31st, 2022. So if you want to continue to try things out, you are welcome to the AI for Science, the AITP reservation is not going to be there, but you still have access to the machines themselves. Secondly, Slack will be available through December 20th, 2022. And what will happen is the materials will start to delete because it's free Slack. So if there are any resources on Slack or pieces of information on Slack that you find helpful, please make sure to go and grab those before the end of this year. As all of you hopefully know at this point, we're offering a certificate of completion and digital badge. The session homework should be submitted by November 15th on the Google form. If you have any questions on homework completion count or like that, or something like that, please reach out to me on Slack. I'm happy to sort of answer questions on that. And something that what you will receive is after you've completed all of your homework, you'll receive a digital badge that actually sort of looks like this. And you are able to show this on LinkedIn, your CV. You can get a digital badge backpack if you want, that you can sort of carry around. And then we'll also send a certificate of completion that looks like this, with your first name and last name, signed by the director of the Argonne Leadership Computing Facility, Michael Papka. So with that, for final things, I just wanted to thank all of our instructors that have sort of discussed and taught us things throughout this series. Along with that, all of our science speakers, all the way back to Nicola at the very, very beginning, for sharing their science and how it applies to AI. And finally, we're going to have a final series survey, so look for that in over email and Slack. We welcome your feedback. The feedback that you give will help make this series even better for next time. And so we always welcome any thoughts, both good and bad, about that you have for the series. So one thing to think about for what's next, this is something I've just talked about a couple times, is if you're interested in any of the research that you've heard about during this series, we have internships for both undergrads and graduates. If you want more information about either of those, you're welcome to find out. We have all sorts of information on the Argonne website. You can use these QR codes or just Google like Argonne internships and things will come up from there. Additionally, for those who are maybe a little bit later in grad school, we also have a huge number of computational postdoc opportunities at Argonne. So if you're sort of thinking about like, okay, what's next after grad school, Argonne and other national labs are super, super interesting and engaging places to work as a postdoc. So that's also something to think about. So with that, I just want to thank all of you for attending and engaging for these 8 weeks of sessions. If you have any other questions about the series, please feel free to reach out to me. And if I don't know the answer, I'll make sure to sort of point you in the right direction from there. So with that, thank you so much for attending. It's been a true pleasure to have all of you so engaged for the past 8 weeks. And I think with that, I will wrap things from there. So thank you all so much.
Thanks, Paige.
Thanks.
Thank you.